Yeah. Hello everyone. Today I will present my MATLAB project on simulation of a 2D compressible lead-driven cavity flow using the simple algorithm framework. The main objective of this project is to solve the incompressible Navier-Stokes equations iteratively using pressure correction and to monitor convergence using residual plots. In this problem, we consider a square cavity where the top wall moves horizontally with constant velocity, while all other walls remain stationary. Due to the motion of the top lid, circulation develops inside the cavity. For incompressible flow, the continuity equation is del u by del x plus del v by del y equal to 0. This equation ensures conservation of mass. The x momentum equation is del u by del t plus u del u by del x plus v del u by del y equal to minus of 1 by rho del p by del x plus nu bracket del square u by del x square plus del square u by del y square bracket close. And the y momentum equation is del v by del t plus u del v by del x plus v del v by del y equal to minus 1 by rho del p by del y plus nu bracket del square v by del x square plus del square v by del y square bracket close. Now the question comes, why simple algorithm? In compressible flow, the pressure does not have a direct governing equation. Therefore, pressure and velocity must be coupled carefully. The simple algorithm solves this problem using the iterative pressure correction approach. The steps are: guess pressure field, solve momentum equations, solve pressure correction equation, correct pressure and velocity, repeat until convergence. Now let's dive into the MATLAB programs. Yeah. So starting with the clear CLC close all. Here I clear all variables, clear the command window and clear all previous figures. Then comes Lx equal to 1, Ly equal to 1. This defines the dimensions of the square cavity. Then comes Ny equal to 51, Ny equal to 51, grid points in X, grid points in Y. These define the number of grid points in X and Y directions. So the computational domain uses a 51 by 51 mesh. Then U lead equal to 1.1.0 moving lead velocity. This is the velocity of the moving top lead. Then comes R equal to 100 Reynolds number based on Lx and U lead. This is the Reynolds number of the flow. At Reynolds number 100, the flow remains laminar. Then comes our rho equal to 1.0, that is density, and nu equal to u lit into Lx by Re, that is kinematic viscosity. Here rho is density and nu is kinematic viscosity. As you can see, now comes iteration parameters, that is max outer iter equal to 3000 and outer total equal to 1.0 e minus 5. This defines the maximum simple iterations and convergence tolerance. Under relaxation, that is alpha u equal to 0.70, alpha p equal to 0.25. This is velocity under relaxation and pressure under relaxation. These are under relaxation factors for velocity and pressure. Under relaxation improves numerical stability and pressure divergence. Then comes pressure correction solver. Max peak core iter equal to 500. Pressure correction SOR limit. Peak or tall equal to 1.0 E minus 5. Inner pressure correction tolerance. Omega SOR equal to 1.75. SOR factor where 1 less than omega less than 2. These parameters are used in the pressure correction solver. SOR stands for successive over-relaxation, which accelerates convergence of the Poisson's equation. Now grid generation. dx equal to Lx by nx minus 1. dy equal to Ly by ny minus 1. These calculate grid spacing in x and y directions. X equal to lim space 0, Lx, nx, y equal to lim space 0, Lx, ny. These create coordinate vectors for a computational grid. Then time step dt diff equal to 0.25 by nu into bracket 1 by dx square plus 1 by dy square bracket close. dt conv equal to 0.45 into minimum of dx dt dy by maximum of u lit eps bracket close. dt equal to minimum of dt diff dt conv. These pseudo-time steps improves numerical stability of the simple iterations. Now field initialization. U equal to zeros ny, nx, v equal to zeros ny, nx, p equal to zeros ny, nx. Initially, velocity and pressure are assumed zero everywhere. Now boundary conditions. Square bracket q, v square bracket close equal to apply cavity bc, comma sorry not comma bracket u, v, u lit bracket close. This function applies cavity boundary conditions. Then comes this sets the top wall velocity equal to the lead velocity. Uh, then comes the simple outer iterations, like for iter equal to 1 colon next outer iter, u old equal to u, v old equal to v. This is the main simple iteration loop. U star v star momentum predictor u v p rho nu nu dx dy dt alpha u star v star equal to L apply cavity bc u star v star u lit. Here provisional velocities are calculated using the old pressure field. Now comes the pressure gradient. dpx RHS pressure correction. Now comes the pressure correction. Div u nu equal to 0 after correction. RHS equal to RH rho by dt into divergence of u star v star dx dy. Then RHS equal to RHS minus mean RHS column. Then square bracket p prime pc res pc its bracket close equal to solve pressure correction RHS dx dy. So this computes the divergence of provisional velocity. If divergence exists, continuity is violated. If divergence exists, continuity is violated. So this point is to be noted. The pressure correction equation is del square p dash equal to rho by del t, del u star by del x plus del v star by del y. Now the pressure correction solver, this one, P prime, comma PC res, comma PC its. This is the pressure correction solver. This solves the pressure correction Poisson's equation using SOR iteration. Then correct pressure and velocity. P equal to P plus alpha P star prime, P prime. This updates the pressure field. P equal to P minus mean P colon. dp dx prime equal to pressure gradient P prime comma dx comma dy. U equal to U star minus bracket dt by rho into dp dx prime. V equal to V star minus dt by rho into dp dx prime. U comma V equal to apply cavity BC bracket U comma V comma U lit bracket close. These equations correct velocity to satisfy continuity. Now residual monitoring. Div nu equal to divergence U comma V comma dx comma dy mass residual iter. This measures continuity error. Mass residual iter equal to norm div nu colon comma 2 by square root num 1 div nu. Well change equal to square root sum bracket u colon minus u old colon bracket to the power 2 plus v colon minus v old colon bracket to the power 2. V norm equal to square root sum, then this one. Then comes mom residual iter. This measures convergence of the momentum equations equal to well change the well norm. Then comes peak core residual iter equal to PC res. Then comes P core iterations iter. P residual iter. This means convergence of the pressure correction equation. Now, if mod iter comma 100 equal double equal 0, iter double equal 1, then this one, then and if iter greater than 20 and n mass residual bracket iter less than outer toll and mom residual iter less than outer toll print. So the iteration stops when convergence criteria are satisfied. Here it is mentioned that the iteration stops when convergence criteria are satisfied. So this code means that after that we printf converts at iteration percentage d dot slash n iter and break and end. Then n iter equal to iter mass residual equal to mass residual 1 colon n iter mom residual equal to mom residual 1 colon n iter p core residual equal to p core residual 1 colon n iter. And then this follows. Then after that we come through post processing. Then you can copy the codes, note down. You can note down the codes. These are the codes. Then comes the local functions. If you think it is too fast that I'm scrolling, you can pause and you can note down the note. You can note down the codes. Also here, this left u equal to Laplacian u j I dx dy. This represents viscous diffusion. Okay, and this conv u equal to u j comma I. This represents convective transport of momentum. That's it. Becomes homogeneous Newman walls. Uh, you don't need to worry. I will just give these codes in the description box. Although if I have missed anything that comes local functions and local functions in this. I told you about lab u, conv u with this. Then this dp dx dp dy equal to pressure gradient p dx dy. This computes pressure gradients in x and y directions. Okay. Value. Yeah, we have come to an end. So now let's run the codes. Let me do one thing. Let me expand the command window so that you all can see it properly. Maximum peak or value, peak or requests are 500, and here the maximum value is 3000. So it has stopped in 3000. Now we'll get the simple residual graphs, velocity field graphs, and no, velocity field is not graph, velocity field contour, I guess, and then center line velocity profiles. Now we'll discuss the results. The first figure shows residual history. The blue curve represents continuity residual. It decreases steadily, showing that mass conservation improves during iteration. Then the orange curve represents momentum residual. It decreases significantly, indicating convergence of velocity field. Then the yellow curve represents pressure correction residual. It converges more slowly because the Poisson's equation is computationally expensive. This one. This is the residual versus iteration graph. Now let's dive into the velocity field contour. This second figure shows the velocity magnitude contour and streamlines. The main vortex forms because the top lead drags fluid from left to right. Right, you can see this from left to right. It is dragging. The streamlines clearly show recirculating flow inside the cavity. Yeah, it's circulating in the cavity. This is what the streamlines are showing. Small secondary vortices are also visible near the corners. Small secondary vortices are also visible near the corners, which is physically expected in lead-driven cavity flow. Yeah, you all can see this. Small. These all will be very small. So this is what velocity field contour. Now let's see centerline velocity profile. This is the third figure that shows centerline velocity profiles. The blue curve represents horizontal velocity along the vertical center line. The orange curve represents vertical velocity along the horizontal center line. These profiles are commonly used to validate cavity flow simulations. This solver has some limitations. The pressure correction equation converges slowly. As you all can see, the pressure correction equation converges slowly. The co-located grid may also produce pressure oscillations. A finer mesh and improved pressure solver could increase accuracy. In conclusion, a simple based incompressible cavity flow solver was successfully developed in MATLAB. The solver correctly captured the vortex structure, velocity distribution, and convergence behavior expected for lead-driven cavity flow at Reynolds number 100. Residual monitoring confirmed the convergence of the numerical solution. So this is it. We have reached to the conclusion. Also, we have got the desired results. So thank you. Have a nice day. Peace.